Hello, discrete math fans. So we showed how to determine if a function is one-to-one when we have finite sets for our domains and arrow diagrams. What about when the domain is infinite? Now remember that we can say that a function f is one-to-one if and only if the following universal statement is true. For all a and b in x, if f of a is equal to f of b, then a is equal to b. So that means if we want to prove that f is one-to-one, we're going to use a direct proof. We're going to suppose that a and b are elements of x such that f of a is equal to f of b. And then what we want to do is show that a is equal to b. Now in order to show that f is not one-to-one, we'll usually find elements a and b in x so that f of a is equal to f of b, but a is not equal to b. So let's run through this example. Let's define f as a function from R to R, the real numbers, by the formula f of x equals 5x minus 3 for all x in the reals. Is f one-to-one? We're going to either prove it or give a counterexample. Now, as a general rule, let's think positive here. Let's try to prove that the functions that we're given are one-to-one. If the proof doesn't work, we'll try to prove it's not one-to-one. So let's let a and b be real numbers and assume that f of a is equal to f of b. This is how we'll always start our proofs about one-to-one. That is, we're assuming 5a minus 3 equals 5b minus 3. Add 3 to both sides, we get 5a equals 5b, and that means a equals b. Therefore, the function f is one-to-one. We started by assuming that f of a is equal to f of b, and then we concluded that a is equal to b. That proves that the function is one-to-one. Now let's try this example. We'll define g as a function from the integers to the integers by the formula g of n equals n squared for all n in the integers. Is this function one-to-one? We're going to either prove it or give a counterexample. Again, we're going to try to prove that it's one-to-one. If it doesn't work, then we'll try to prove it's not one-to-one. So let's let m and n be integers and assume that g of m equals g of n. That is, we're assuming that m squared is equal to n squared. All right, now here's where we're going to get stuck. If we know that m squared is equal to n squared, we cannot conclude that m equals n. Well, why not? Well, what happens if m is equal to 2 and n is equal to negative 2? Well, then m squared is equal to n squared, but m is not equal to n. Well, look, that gives us our counterexample. Therefore, g is not one-to-one. So in the process of trying to prove that the function is one-to-one, we come up with a counterexample that actually shows it's not one-to-one. And that's it. Okay, that's all for now.